So we just looked at relative risk as a measure of association when you have two binary categorical variables. Well, what happens when you have two numerical variables? How do you find a measure of association? Well, a very popular and commonly used measure of association for two numerical variables is something called covariance. So consider two variables, x and y. Covariance asks, is y larger or smaller when x is larger? The shorthand for covariance is COV x comma y with parentheses around x comma y. How do we interpret covariance? Well, if covariance is greater than 0, then this implies a larger x will lead to a larger y. If covariance is less than 0, then this suggests a larger x will lead to a smaller y. To put it another way, covariance gives us the direction of a linear relationship between two numerical variables. The problem with correlation is covariance is it only gives direction. So that's why we want to standardize covariance to create correlation. So the correlation for a sample is denoted as follows. So we have a sample covariance of x and y, and we divide by the sample standard deviation of x times the sample standard deviation of y. The units of x and y cancel out, and by standardizing by the sample standard deviation of the two variables, we restrict the range of correlation to -1 and +1. And we denote correlation for a sample with lowercase r subscript x, y. We can also calculate the correlation for a population. It's a similar kind of calculation, in fact identical, except that we use Greek letters to refer to a population covariance, a population standard deviation, and a population standard deviation for y, for both x and y. So we denote the population correlation using the Greek letter rho, lowercase rho, which is similar to lowercase r in Latin or Roman letters. The basic idea is we standardize the covariance. We can use a sample covariance or a population covariance, and either way, we're standardizing it. The correlation coefficient is a very useful numerical summary. Unlike covariance, it gives both the strength and direction of a linear relationship between two variables. So one nice thing about correlation is that it's very easy to interpret. The sign indicates the direction of the relationship, either negative or positive, and the correlations are bound between -1 and +1. The absolute value of a correlation coefficient will give you the strength or magnitude of that linear relationship. So -0.8, it's actually stronger than 0.4, has a greater magnitude because the absolute value of -0.8 is 0.8, which is larger than 0.4. So we have these measures of association for numerical variables, covariance and correlation. Covariance is a useful building block, but correlation is more commonly used in published research and in scientific articles.